to one singular force of tension. Okay. And so we can see right away, well, of course we have circular motion, so there will be a centripetal acceleration. We have this diagram, which is showing us an angle, and this is going to be one of the questions we need to answer. Angle theta with respect to the vertical. So theta shows up right there. And I'll just kind of do one of these. There's theta, right? So I believe I can get to work as long as I have more information. I need to understand a couple things. There is a radius of the circle, right? And so radius is 12 meters. I am also told that the velocity is a constant speed. Remember, we're going to be dealing with that situation. 25 miles per hour is our speed. So the first thing I want to do is I want to look at the centripetal acceleration and find that. So I have radius, I have velocity. It should be straightforward. However, I don't like these units, so I'll do a conversion, and I will end up getting just about 11.2 meters per second. I'm going to save that work for you. It's very straightforward stuff. So now I have units that jive, and I can get right into a solution. So centripetal acceleration. I know that it is velocity squared, or speed squared, divided by radius. So I have 11.2 meters per second squared, and my radius is 12 meters. And when I do that math, right around close to 10.5, right? Meters per second squared. That's it. That is the centripetal acceleration. The acceleration toward the center of the circle. And it's interesting to note that it's pretty close to the value of g, right? So if g is 9.81 meters per second squared, right? Well, this acceleration toward the center is sort of in that ballpark. And what that means is riders will experience that inward acceleration, but really what they're going to feel is they're going to feel like they're thrown outward, but they're going to feel like they're thrown outward at this rate of acceleration. And so it'll be quite noticeable, enjoyable, not very harsh, but noticeable, and makes it a good ride. But that's it for part A, right? We've answered that question. Check. Now, how about that angle? So let's get started on that. Do it this way so we can see everything a little better. Go to part B here for that angle theta. So there is an acceleration toward the center of the circle, which, with the way I've drawn this, toward the center of the circle is this way, right? So there must be a net force acting in that direction. So I don't want anything over here canceling it. However, I do want something canceling this downward force of gravity. I need something upward. I don't want any up or down acceleration during the ride. Not for this ride. So there's going to have to be something there, right? And it has to be enough to cancel this. So think about this for just a moment before we continue. The heavier the rider is, let's say you're talking about an adult versus a child. The adult's heavier, larger downward force. There must be this larger upward force to compensate. And that comes from that tension in the cable. So let's work that out, right? So what I have basically here is the y component. No big deal there. And what I know is that the sum of the forces in the y direction need to be 0. But those forces are the force of tension in the y direction, and that's in the positive y direction, and in the negative y direction, mg. And when I do that, I should get 0. So therefore, force of tension times cosine of theta equals mg. And I chose cosine because if I look at the way this triangle is drawn, right, this is the component of tension that I'm looking for, and it happens to be adjacent to theta. So adjacent means cosine. So there's no confusion there. But I have an issue And the issue is that angle theta is an unknown, but so is Ft, force of tension. I have two unknowns here. So at this moment I cannot solve. However, what I can do is look at the x direction. And when I sum the forces in the x direction, I do not want 0. I need that centripetal acceleration to result. So this is going to be equal to the force of tension in the x direction, and that's it. That's that guy right there. That's it. And that is equal to the mass times the centripetal acceleration, right? Newton's second law happening right here. But this is also the component of tension. Oh, another bell. So that component of tension happens to be the force of tension times the sine of theta. And so, all right, it looks like I have two equations with two unknowns. Except mass is also an unknown, isn't it? We weren't given any mass. I wonder what's possible here. So let me try something here. Let me try. I'm going to look at this. And I'm thinking, you know what, in this guy, what if I just solve for the force of tension and see where that takes me? Okay, I'm gonna try stuff. That's what you have to do quite often, is simply give something a shot and see where it leads you. When you do this, I'm solving this for force of tension, by the way. What you end up with is mass times centripetal acceleration divided by sine of theta. All right, now I have this unknown in this equation also. So what if I just did a substitution here into that one? And let's see what results. Substitute. And so I'm going to rewrite this, but I'm going to do the substitution right away. Let's see what happens here. All right, and then cosine of theta, and that's going to equal mg. So first things first, right away, mass cancels out. I don't need to know the mass, and that's super convenient. I don't know the mass. But it also should remind you of other situations where mass cancels out. Anytime there's an object accelerating due to gravity, all objects accelerate at the same rate because of gravity, or when it's gravity causing that acceleration. So maybe no surprise, or maybe just kind of an interesting coincidence. But here we go. We're looking for angle theta. We have acceleration toward the center of the circle. We know what g is. We're looking for theta. I've got a sine and a cosine, and in fact, I rearrange this to look like this. Okay. Now, maybe at first glance you don't notice anything. Maybe you do, because what happens here, am I allowed to just flip this? Well, yeah, if I flip this, but I also got to flip the other side too. Take the reciprocal of both sides, and I end up with sine theta over cosine theta times 1 over centripetal acceleration equals 1 over g. And this is kind of cool because this resolves into tangent. And if I multiply both sides by ACP, then that goes over there. See what happened right there? That just resolves. And multiply that. And this is looking pretty awesome. Totally solvable. I'm going to say theta is going to be equal to inverse tangent of that business right there. Right? So now I just have to plug in some numbers. And my centripetal acceleration was 10.45 meters per second squared. Keep track of your units, people, please. And g is 9.81 meters per second squared. So this angle, check this out. This is, at this point, maybe worth just mentioning real quick. Angle theta seems to be related to this ratio, the ratio between the centripetal acceleration and g. and related through the tangent function. So what we get when you do this is theta seems to be equal to, depending on how many sig figs you like, 46.8, about 47 degrees. So we've answered that question about our situation also now. So I can come back here and I can go check. All right. Now the last question, part C, question C, was really about mass, and it wants to know how come. What is the role of mass here? What if there was a heavier rider, an adult versus a child? What happens? Does theta change? Does the centripetal acceleration change? And the answer is no. Both weight and the centripetal force, the force which ends up changing the direction of the chair with the rider, they both depend on mass in the same way. And what ends up happening, as we saw here, mass cancels right out. It's gone. It doesn't matter how much the rider weighs. All the chairs will be at the same angle with respect to the vertical. And you can observe this. When you go to an amusement park, you go to Knott's Berry Farm, Magic Mountain, doesn't matter. Look at one of these rides and notice that chairs that have riders and chairs that are empty both sort of make the same angle with the vertical. It doesn't matter whether there's a rider. Some interesting stuff. One last thing for you. One last thing. Okay, so check this out. Bells. I'm hearing bells. Okay, this is going to take just a moment because I'm not doing this one for you. But I want to bring this one up. Question 110. All right. I want you to take a look at this question. And it's a good one. I don't think it's super difficult. Not really. And I just want to give you a hint. Okay? A hint for this question. I want you to draw free body diagrams for each position. There are positions A, B, and C that are illustrated in the question. You'll see what's going on. As soon as you read the question, this is going to make total sense to you. So try to solve question number 110 on your own and do it with this method, okay? And I bet you come up with it. I bet you're going to have not too much difficulty at all. But if you do, let me know. Thanks for watching. See you next time.